In previous videos, I've started to talk about how modeling a system analytically involves making a number of assumptions and simplifications. We've done some talking about how you can tell what simplifications are acceptable and which simplifications are not acceptable. Today, I'm going to start showing you a method for analytically modeling systems that will make your job much easier. It's based around the concept of a block diagram. A block diagram is a kind of a sketch that we use to show what the inputs and outputs are of a system and how one system relates to another. In a block diagram, we use a block to represent a system. Each block receives an arrow as an input and an arrow as an output. Each of these arrows represent a signal. The arrow coming in is the input signal, and the arrow going out is the output signal. The block diagram becomes a powerful tool that we can use when we recognize how systems relate to one another. In other words, a single system might be able to be broken down in such a way that the output signal from one system is the input signal to another system. We can make our modeling job much easier by modeling each piece of the system individually. To explain how this works, I'm going to show you an example. In class, we've been working on modeling the little electric car. We saw how we could simplify this system in different amounts. With each iteration of simplification, we reduced the number of elements that we were taking into account. We saw that we could simplify the system as just a mass, or as a mass with wheels. Or we could become more complex, model the system as a mass on wheels with a motor. I'm now going to represent this idea as a block diagram. I'm going to start with the most simple simplification that we had, where we had a mass on a surface with a force as the input and with the velocity as the output. If I draw this as a block diagram, I will have a block, and I'll call that block the mass. The output of this simple system is the velocity, and the input is an applied force. Now, let's suppose that we want to make this simplification slightly more complex by adding in the idea of wheels. Let's look at just a wheel by itself. This wheel will rotate with some angle theta, and as the wheel rolls, it will translate. If the wheel is accelerating, it will exert some force at its axle, which I'll call P. The wheel will also have some friction. Now, what I want you to see in this diagram is that the applied force that we drew in the previous diagram, Fa of t, is the same quantity as the force that we've drawn in this wheel as P of t. If this wheel was physically attached to the bottom of this mass, and the wheel was driving the mass as it is in the electric car, then the force P of T is the applied force Fa. I'm going to change the label on this to represent that fact. Since the applied force signal, which is the input to my simple mass diagram, is the same as the force that I've drawn on this wheel, I can add the wheel as a block in my block diagram. In this case, the applied force is the output signal to the wheel and is also the input signal to the mass. That's why I can draw the blocks connected together like this in the block diagram. Now, in the wheel, I haven't yet drawn any kind of an input signal. What might the input signal to the wheel be? If our goal is to ultimately model the little electric car, I might want to make the input signal be a torque. I'm going to draw that in the block diagram. Now, one piece of the electric car system that we haven't shown yet is the motor. Could I add the motor onto my block diagram? If I can identify the torque on the wheel as the output signal to my motor, then I can add on the motor like this. The torque over time, which is the input to the wheel, is also the output from the motor. What is the input to the motor? Well, the input of our overall system that we wanted was voltage. Since the input to the motor could be voltage, I can add that as the input to my complete block diagram. We've now drawn a complete linkage that takes us from the input that we wanted to begin with, the voltage, all the way to the output that we wanted, the velocity. We've broken down the complete system, the electric car, into three components: a motor which converts voltage to torque, a wheel which converts torque to applied force, and a mass which converts applied force to velocity. My modeling process has now been made easier because all I have to do is find an equation that models each of the blocks in this block diagram relating the input signal to the output signal for that individual block. In the next video, I'm going to walk you through the process of finding each of these equations and relating them. Rather than just modeling the car for you, I would like to instead break up the car into categories of things that can be modeled in similar ways. That way, hopefully in the future, when you have to do a modeling task, you can first identify what sort of thing it is that you have to model, and then identify the approach that you could use to model that thing. So instead of just modeling the wheel of the little car, I'm going to expand that category, and instead we're going to have a whole video on how to model rotating things. We'll see that wheels are not the only rotating things that you can model, but that the procedure for modeling things that rotate is very similar. Also, rather than just modeling the motor, although we will model the motor as well, I'd like to model in general circuits and also things that have both electrical and mechanical components. These kinds of systems will use similar laws in the modeling process. The third part of the block diagram that we drew was the mass. We already looked at how to model a sliding mass and also a mass spring damper system, so we won't have another video on that part. Rather, today's video is going to focus on the topic of rotating things. The first example that I'm going to show for rotating things is a wheel rolling on a surface. Here, I'm also going to expand on how to deal with rolling resistance. We spent a little bit of time trying to research this in lab, and today I'm going to show you a way to deal with that rolling resistance. The second system that I'm going to model today is the system of a rod that is attached to the ground by a hinge. And this rod is free to rotate on the hinge. By watching the modeling of these two systems, my hope is that you'll see what the commonalities are when we're dealing with rotating things. So let's start out with the wheel. Before we move on to a wheel rotating and rolling along the ground, let's look at a couple principles of rotating things with the wheel rotating freely in space. Let's suppose that the wheel has a pin at the center so that it's free to rotate but not free to translate, that is, to move linearly in space. We would generally represent the angle of rotation of the wheel with the variable theta, and this would be a function of time. That would make the speed of rotation of the wheel be the derivative, theta dot, or this is often represented also as omega. Then, the angular acceleration of the wheel would be theta double dot. That would be the same thing as omega dot, and that would be the same thing as alpha. The letter alpha is often used to represent the angular acceleration. Now, this wheel is not a massless wheel. It has some mass. The mass of the wheel gives it inertia, but the mass of the wheel not only gives it linear inertia, that is a resistance to acceleration linearly, it also gives it some rotational inertia. The letter J is typically used to represent the moment of inertia. Conceptually, the moment of inertia is an expression of how difficult it is to get an object spinning or rotating. The moment of inertia is different depending upon both the shape of the object and the axis around which the object is rotating. For example, suppose that we want to rotate this disk around its vertical axis so that the disk is spinning around this axis like that instead of rotating around its center. If we spin the disk in that way, then its moment of inertia is calculated as the mass times the radius of the disk squared divided by 4. On the other hand, if we spin the disk around its center so that it rotates like this, Then, the moment of inertia is calculated as the mass times the radius squared divided by 2. This means that for the disk, if we try to get it to spin in a way that it would if we were rolling it, it is twice as difficult to get the mass rolling as it would be if we were trying to spin it around its x-axis or y-axis like this. Typically, we would figure out what the moment of inertia is for the particular spinning thing that we're looking at by looking it up in a table. Here's a table of moments of inertia that I found on Wikipedia. They're using the letter I to represent the moment of inertia. This table shows a particular shape as well as the axis around which that shape is being rotated on the left, and it shows the corresponding equation for the moment of inertia on the right. I encourage you to take some time looking through a table like this and see what conclusions you can come to about the resistance to rotating that different shapes have around different axes. For now, with the information we have here, we can write some equations about the disk. When we were modeling the mass sliding across the floor, we summed the forces and set them equal to the mass times the acceleration. With rotating things, we'll do a similar kind of a task. Instead of summing the linear forces, we're going to sum the rotational forces. Rotational forces are known as torques. And instead of saying the mass times the linear acceleration, we'll say the moment of inertia times the rotational acceleration is equal to the sum of the torques on the disk. So what kinds of things might apply torques to the disk? Well, one thing that might apply a torque is any kind of resistance due to a bearing. I can write bearing friction here, and I'll draw it as a curved arrow to show that this is actually a torque, so I should write it as a torque. If the wheel is touching the ground, we might also have some friction, and that friction would be applied at the bottom. Anytime we have a force on the wheel that is applied not as a torque, but as a linear force, we have to take into account the distance around the center of rotation at which that force is being applied. Let's suppose that the radius of this disk is r. In this case, we would have a force being applied at a distance of r. So the torque on the wheel due to that force, let's call this friction, is equal to the amount of force applied, let's call this the force of friction, times the radius. Now, let's expand our wheel to not simply be rotating in space, but to actually be rolling along the ground. Many of the aspects of the wheel rolling along the ground are the same as the wheel spinning in space. This wheel is rotating, and it has an angle theta. And since it's rotating, we also have to think about its moment of inertia. One of the differences between a wheel rotating in space and a wheel rotating along the ground is that this wheel also moves in space. It has a linear displacement. The equivalent to theta for linear displacement is x. And we know that x dot, the derivative of its position, is what we also call the velocity, and that x double dot is the derivative of velocity, which is the same thing as acceleration, that is, linear acceleration. Also, if we know that this wheel is rolling and not slipping on the ground, we know that there is a relationship between x and theta. I'm going to draw a dot at the center of this wheel so that I can indicate the radius of the wheel. If the wheel is not slipping, that means that there is a defined relationship between theta and x. The relationship is that x of t is equal to theta of t times the radius. We could also take the derivative of both sides of this equation to find that x dot of t, that is, the velocity, is equal to theta dot of t times r. And we could take the second derivative, these relationships are true as long as the wheel is not slipping along the ground. A second difference between a wheel spinning in space and a wheel rolling along the ground is that we have both rotational and linear motion, and that means that we have to use both of our force summing equations. We have to sum both the linear forces and the torques. Now, as we start to model this wheel rolling along the ground, we must remember that what we're doing is modeling a system. And that means that we need to start by identifying what the input and the output are in this system. In this particular case, I'm going to say that the input is a torque, and this is a torque that is applied, let's say, by a motor. So I'll call it torque applied. I also have to identify the output. In this case, I'm going to identify the output as the velocity, the linear velocity of the wheel as it rolls along the ground. So the output is going to be x dot of t. I'm going to now rename this. Since my output is a derivative, I would prefer to have my output simply be a variable and not a derivative variable. So I'm going to say that the output is v of t, and I'm going to rename this not as a position but as a velocity. Now, I still haven't drawn one other force here, and that is the force of friction. Now, let's go ahead and model this wheel rolling on the ground. Since this is a rotating thing, we know that we can sum the torques. Since the wheel is moving linearly as well, we also know that we can sum the linear forces. Let's go ahead and do both. First, let's sum the linear forces. The mass times the acceleration, v dot, is equal to negative force of friction. In this case, this is the only force that we have. I know that this seems counterintuitive because we also have an applied torque. But remember that right now we're only summing the linear forces. The torque is a rotational force, and we will account for it when we sum the torques. So let's go ahead and do that now. Let's sum the torques. Instead of having mass times rotational acceleration, we have j, the moment of inertia, times the rotational acceleration is equal to the sum of the torques. we need to make sure that we get the right signs on everything here. We've defined the linear positive direction as being to the right. We've defined the rotational positive direction as being a clockwise rotation. The torque that is applied here is also a clockwise torque, so that sign will be positive. Now, we also have a torque being applied due to the force of friction. The force of friction is being applied at the bottom of the wheel, not at the center of the wheel. So, in addition to providing a linear force, it also provides a rotational torque. The amount of rotational torque that is applied by the force of friction is equal to the force times the radius. We know that in general, any kind of a torque is equal to a force and the cross product of that force with the radius. Here, the force of friction is being applied at a 90-degree angle with the radius, so that the cross product will be entirely in the direction of the force. So, to get the torque, we'll take the force of friction and multiply it by the radius. Now notice that I made this be a positive sign. That's because the force of friction we've drawn to the left. If the force of friction is being applied in this direction, the direction of rotation that will be caused will be a clockwise rotation, and that is the direction that is positive for our rotation. That's why I made the force of friction be positive in this equation. Now, we are trying to come up with a relationship between our input and our output. The input is the torque, and the output is the velocity. In this equation, one thing that we do not know is the force of friction. Other things, the radius, the mass, and the moment of inertia, are all defined by the properties of our system. However, one additional piece of information that we know about this system is that the wheel is rolling without slipping. When the wheel is rolling without slipping, that gives us a relationship between theta and v, or x, the direction of motion. This relationship is that the linear velocity of the wheel will be equal to the rotational velocity times the radius. Since the wheel is rolling without slipping, we know that the amount of force of friction in this system is exactly that amount of force of friction that is needed in order to keep the wheel from sliding. So we can use our equations here to figure out the value of the force of friction. Then we could plug that value back into the other equation to give us one equation with two variables. And we want those two variables to be velocity and torque, because those are our inputs and our outputs. Let's go ahead and do that right now. The first thing I'm going to do is plug in this relationship into equation 2. We'll call this equation 1, and we'll call this equation 2. The next thing I'm going to do is expand the moment of inertia. Remember, we learned earlier that the moment of inertia for a disk rotating around its center is equal to mr squared over 2. The moment of inertia for a disk rotating around its center is 1/2 mr squared. Next, I'm going to do a little bit of simplification by getting the r's all on one side of the equation. And I'm also going to get the 1/2 onto the right side of the equation. Now, I'm going to go back and I'm going to use equation 1. Equation 1 gives us a relationship between mv dot and the force of friction. I'm going to plug that equation in to the left-hand side of this equation so that I get the negative force of friction is equal to everything on the right-hand side of this equation. Finally, I'm going to go through one last simplification to get all of the forces of friction on the left and the torque on the right. This equation, which I'll call equation 3, gives us a relationship between the applied torque and the force of friction that is necessary in order to achieve rolling without sliding. If we assume that the only friction in the system is that which is required to keep the wheel from sliding, then this is the amount of friction that there is in the system. Notice that when the applied torque is 0, the force of friction is also 0. This is a clue that this equation might be correct, because we know that if no torque is being applied, no force of friction is needed in order to keep the wheel rolling. Now, let's take this relationship between friction and torque and let's plug it back in to our first equation. Now we have an equation that relates our velocity to the torque. You might notice that this is not quite a first order system. In order for this to be a first order system, we would also need a term in here with the velocity. In real life, there actually is another term in here that is multiplied by the velocity. That term is due to resistance, like rolling resistance and friction, that is dependent upon velocity. Here, we've only taken into account the friction that is necessary to keep the wheel rolling, not the component of friction that is proportional to the velocity. There is also wind resistance that also increases in magnitude as the velocity of the rolling object increases. So in this case, we've simplified this system to be not quite a first order system, when in fact, in reality, the system is first order. Sometimes the way that we deal with this is instead of trying to actually model all of the factors that are individually proportional to velocity, we'll add in a second term with a single coefficient that represents everything that is proportional to velocity: rolling resistance, friction, and air resistance. And we'll simply write it out like this. Then we would determine the value of B, not analytically by modeling things like wind resistance, rolling resistance, and things like that, but we would test the system and empirically find the value of B. This is one of the cases in which we often mix together empirical and analytical methods to model the system correctly or in a way that accurately represents reality, while leaving out the most complex parts of the analytical modeling. Next, we're going to take a look at another rotational system, a rod on a hinge. We're going to look for similarities between these two rolling examples, the free rotation example and the wheel rolling on a surface example, to see some commonalities in rotating systems. Next, let's look briefly at another rotational system, a rod on a pin. In this case, I'm going to say that the output of the system is the angle of the rod with time, and I'll define that angle here. As the input, I'm going to suppose that we are applying a torque to the system like this at the pin. So our goal is to find a relationship between the input, the torque, and the output, the angle theta. The first thing that we want to do in this case is to identify all of the forces and any additional torques that we have on the system. In this case, we have a gravitational force that's being applied at the center of mass. I'm going to right away identify that force as being equal to the mass of the rod times gravity. Next, because we have a pin, we'll have some kind of reaction forces that are typically labeled with the letter N for normal force. We'll have one normal force in Y and another normal force in the X direction. Now, let's write some equations. Similar to the wheel that was pinned at the center and not allowed to translate, this rod is also not allowed to translate in any linear direction because it's attached to its pin. So, to derive the equations for this system, we only have to sum the moments. In order to sum the moments, we have to first decide which point around which we will sum them. I'm going to choose the point of the pin because we have a torque that's applied at that point. Now, we sum the moments by beginning with J times theta double dot. Remember, this is the equivalent of mx double dot in linear motion. The torque is in the same direction as theta, so that will be positive. Now, we also have to account for the force of gravity. The force of gravity is causing a torque around the pin point. But remember that a torque is the force crossed with the radius. In this case, the force of gravity mg is not entirely in the direction that is perpendicular to the radius. We have to find first the component of gravity that is perpendicular to the radius. That is the force of gravity that will cause the torque. Next, I have to decide if this component is the sine of theta or the cosine of theta. I can see in my diagram that while this angle is theta, this angle here is also theta. So the component of the force of gravity, which is perpendicular to the radius, is the cosine. I can check my work by imagining this rod in different positions. When the rod is straight up and down, the gravity causes no torque at all. In that case, theta is equal to 90. I need to check and make sure that the cosine of 90 would then be 0. And I can see that the cosine of 90 is 0. That means that when the rod is straight up and down and theta is 0, this term will go away. On the other hand, when the rod is straight out like this, theta will be 0. In that case, the entire force of gravity will be entirely perpendicular to the radius and will be causing maximum force. So this term should be at its maximum value. Since the cosine of 0 is 1, I can see that this is correct. Now I still need to multiply this by the radius. In order to do that, I have to label what the radius is in my diagram. I'm going to call this distance L so that I can multiply it over here. Since my output is theta and my input is torque, I'm actually finished with my equation right now. However, I'm going to go one more step and fill in the moment of inertia. To find the equation for the moment of inertia, I'm going to go to my table. I want to find, first of all, an object that is the same shape as my rod. Here are a couple of rods. I have to decide which of these to use based upon the axis of rotation that my rod is using. In this picture, the rod is rotating around its center. That is not the case in my example of a rod on a pin. In our case, the rod is rotating around its end, so I want to use this equation for moment of inertia. In this equation, the table is using the capital letter L to represent the length of the rod. In our case, we defined half the length of the rod as a lowercase l. So capital L in this equation is 2 times L in our equation. I'm going to plug this in. Now I'm going to rearrange the equation a bit so that the output, theta t, is all on the left-hand side and the input, the torque, is all on the right-hand side. Similar to the last example, this equation is not quite a second-order equation because there's no theta dot in the equation. In reality, there really would be a theta dot, and that term would come from the resistance of the bearing or the hinge. We can, similar to the last case, put in a term that is proportional to theta dot and is going the opposite direction as the torque. We would find the value of the coefficient for this term experimentally. Now, do you notice anything about this equation that we've learned about in terms of system properties? You may notice that this equation is non-linear. Here we have a term that is the cosine of theta t. Do you remember what the implications are of a system that is non-linear? This system will not follow the superposition principle. Because this system does not follow the superposition principle, it makes it quite difficult for us to find the output to any kind of an input, which is generally our goal in our systems modeling. The way that we typically deal with a system that is non-linear and therefore does not follow the superposition principle is by restricting the range of operation of the system. Now let me show you what I mean. If we go back and look at our diagram of the pinned rod, there are times in a real system that uses a pinned rod where we can safely assume that the pinned rod most of the time stays around the upright position. In other words, the rod never gets very far away from straight up and down. Can you think of some real systems that operate similar to a pinned rod? One example is a Segway. Another example is a unicycle. In fact, another example is a person standing on their legs. All bipedal motion operates somewhat similar to a pinned rod. Both biological bipedal systems like people and also robotic systems when we try to make a robot that stands and walks on two legs. In all of these cases, most of the time when the system is operating, the rod, that is the body of the robot or the person standing on the Segway, is nearly upright. The case where the rod gets far away from its center position is a bad kind of a situation, because it means that it is falling over. Now, if we can safely assume that the rod is almost always nearly up and down, that allows us to make a simplification in our system that will make it linear. When the value of theta is close to 90 degrees, the value of the cosine of theta is close to 0. So when theta of t is approximately equal to 90 degrees, the system can be approximated without this term in it. Of course, this will only work as long as our assumption is true. If we want to have a linear system that accounts for other angles besides those that are close to 90 degrees, we can simplify this system around other angles. For example, we could simplify this system around an assumption that the angle is approximately 45 degrees. We would simply evaluate the cosine of 45 degrees and plug it into this equation. We would then not have a cosine of a variable. This whole term would be a constant. Our new simplification would then be accurate only in those cases when theta is approximately 45 degrees. We could repeat this process and find a different system model for each angle that we want to be able to have the system operate in. Then, when we write some code to control our system, we could have a series of if statements, checking to see what the value of the angle is, and setting the system model appropriately to that particular angle. This process is known as linearizing a system. Linearization is very useful because nonlinear systems are so difficult to solve. Once the system is linearized, as long as our assumption holds about the approximate angle at that time, the superposition principle will apply within that range, and the system becomes much easier to solve. We've now looked at a couple of rotational systems: a wheel spinning in free space, a wheel rolling along the ground, and a rod that is pinned. In each of these cases, we summed the linear forces if the system was allowed to translate in space, and we also summed the moments as long as the system was allowed to rotate. We then used the equations to come up with a single equation relating the input variable to the output variable.